Hello students and welcome for the machine design 2 lecture. Today we will start our new section, or you can say new topic, that is a flywheel. Okay, just a minute, I will share my screen. Okay, so everybody might be aware with the application or use of the flywheel. So in this lecture series, we will discuss the basic function of the flywheel, then how it can be store energy, then how we can go in for a design. Obviously, as a design part, we need to understand um, the basic dimensions and all the things. Okay, so let we can start our with the introduction. So basically, the flywheel is which is nothing but is a we can use it is as a reservoir to store the energy, because in a four-stroke, or you can say IC engine, in a particular period, the supply of energy is more, and uh, when the excessive energy is released, now that energy we need to store in somewhere. So uh, that energy we can utilize for further operations. Okay, so here nothing but is that we can store that energy which is created uh, particularly at a power stroke, and which can be used further to develop suction stroke, compression strokes, and exhaust strokes. So in four-stroke engine, generally the power stroke is provide created energy. At that time, the successive exceeds or excessive energy is generated, which is stored in the flywheel, and that energy can return to the engine when for completion the remaining three strokes, that is suction, compression, and exhaust. Now this excessive energy developed during the power stroke is absorbed by the flywheel and released to the crankshaft during the other strokes. So now there is no energy is developed, thus the rotation of the camshaft at uniform speed. A little consideration will be shown that when the flywheel absorbs energy, its speed suddenly increases, and when it releases, the speed get decreases. Hence, the flywheel does not maintain a constant speed. So this point is very important while designing the uh, crankshaft. Sorry, designing the flywheel as well as crankshaft, because the fluctuation in energy is occurred due to the energy variation. Okay, so simply we can say the fluctuation of speed can be occurred because of that, and that fluctuation of speed we can mitigate by using a gearbox. In machines where the operation is intermediate, like punching machine, shearing machine, riveting, crushers, etc., the flywheel stores energy from the power source, and a great portion of the operation cycle, and it gives up back during the small period of the cycle. So the energy from power source to the machine is supplied practically, but which is transmitted to in a constant rate through the operation. But to the flywheel, with respect to the flywheel, the energy is always fluctuating. Now we can see some coefficients of the fluctuations of the speed we need to calculate, because we need to understand how much the fluctuation is occur. The difference between the maximum speed and minimum speed during the cycle is called as a maximum fluctuation in the speed. The ratio of maximum fluctuation of the speed to the mean speed is called as a coefficient of the fluctuation of the speed. Okay, you can just go through the equations So finally, how we can calculate it? The mean speed we can calculate by maximum speed during the cycle, my plus minimum speed during the cycle, and divided by 2. That is nothing but the mean. Now the coefficient you can find out n1 minus n2 divided by n, or you can considering with the angular velocity, then you can omega 1 minus omega 2 divided by omega, or if you are going with the linear velocity, v1 minus v2 divided by v. The coefficient of friction of the speed is limited factor in the design of flywheel. It varies depend upon the nature of the service or application to which the flywheel is employed. Now we can go with the different values of the coefficient of the friction for a particular machines. So these are the particular values coefficient of fluctuation in the speed. If we observe the different type of surfaces, or you can say different type of applications, the variation is more. When we go with the electrical machines, the variation varies too much minor. And when we go with the mechanical, heavy mechanical machines, such as that crushers, so here the fluctuation is near about 20%, near about 20%. Even the hammering machines, there is also near about 20%. So based on the application, the fluctuation of the speed get varied. Now, how that fluctuations can be occur? The fluctuation of energy may be determined by turning moment diagram, which is shown in figure number 1. For a complete one cycle, or you can say complete cycle of operation, one complete cycle can be done with a 360-degree rotation. Now, considering the turning moment diagram for single cylinder double acting steam engine, which is shown in figure number 1, the vertical coordinate represents the turning moment and horizontal coordinates that represent the crank angle. Okay, you can see in x-axis and in y-axis. A little consideration to be shown that the turning moment is 0 when the crank is at 0 degree, or you can say at starting condition. It arises to the maximum value when the crank angle reaches to the 90 degree, and it is again come to the 0 when the crank angle is 180 degree. This shows that the curve ABC, small ABC, and it represents the turning moment diagram for outward stroke. The curve CDE is the turning moment for in stroke, and somewhat it is near about similar to the curve ABC. So nothing but in the turning moment diagram, both curves are look like a same. Okay, so since the work done is in a product of the turning moment and the angle of turn, how much angle it rotate, therefore the area of turning moment diagram represents the work done per revolution. In actual practice, the engine is assumed to be work against the mean resistance torque as shown in horizontal line AF. The height of ordinate small a capital A represents the mean height of the turning moment diagram, since it is assumed that the work done by the turning moment per revolution is equal to the work done against the mean resistance torque. Therefore, the area of resistance small a, capital F, small e is proportional to the work done against the mean resistance torque. Okay, so the total area belong a rectangle which is shown with the blue line, you can see in figure number 1. So that is the total area of the work done. Now, the main resistance torque, that line is AF, cuts the turning moment diagram into two segments. Okay, upper segment, lower segment. and at a particular points, that is a B, C, D, E respectively. The crank moments from A to P, small a to P, the work done by the engine is equal to area A capital B small p, okay, which is shown over here. It's a small curve, okay. Whereas the energy required is to represent by the area small a, capital B, and P. So you can just concentrate over this segment. Just a minute, I will show you. Okay, you can concentrate on this area. I will change the line. Okay, you can concentrate, sorry, you can concentrate in this area, small a, capital B, P and A. So this is total work required, and the actual work done is given by this area, given by this area. Okay, so I hope you have understood. Now the amount of energy to be taken from the flywheel, and hence the speed of the flywheel decreases. Now the crank moves from P to Q, and work done which is equivalent to PBBCQ, that is PB. Just a minute, we will highlight that. This is PB, then C and Q. So that much is the work. Okay, so area the required for energy represents by PVCQ. Therefore, the energy has been more work than the required. This excessive work now we have to store, that will be stored in a flywheel. Hence, the speed of a flywheel increases while the crank moves from P to Q. Similarly, when crank moves from Q to R, more work is taken from the engine and then it is developed. The loss of work is represented by area CCD. To supply this loss, flywheel gives up some of the energy from inner to the crank, so it can change its speed. As the cranks moves from R to S, the excessive energy again deployed, developed, given by the area DDE, and the speed again increases. As the piston moves from S to E, uh, again there is a loss of work and the speed decreases. The variation of this kind of energy increasing and decreasing, it means that it moves from the mean resisting torque line, that is called as a fluctuation of energy, okay, which is we can see in the figure number 1. Now the small consideration has to be shown in figure number 2. The energy is the maximum while at point Q or at point S. There is due to the fact that flywheel absorbs the energy while the crank moves from P to Q, and it again moves from R to S. On the other hand, the engine has minimum speed required at P to Q, P or at R. The reason is that the flywheel gives gives out some of energy to the crank, and which can move from A to P and from Q to R. This difference between this maximum energy difference is called as the maximum fluctuation of the energy. Now look at the turning moment diagram for four-stroke IC engine. Okay, here they basically we need energy in this whole segment, in the whole segment we need energy. Okay, the energy is only generated during this period. Okay, this is a power stroke. You can say, you can just look the various sections of the stroke: suction, compressive, then working, that is a power stroke, and exhaust stroke. So this line is a mean line, and above that the excessive power has been generated, and that power we need to be stored. Okay, so to perform the other operations, we need to energy from the flywheel. Okay, that is shown over here. Okay, let's see. So in the turning moment diagram, figure number 2, we can see the four-stroke internal combustion engine, where the four-stroke which is occurred, that is in a single working cycle through the angle of 720 degree, that is a 4 pi radians. Since the pressure inside the cylinder engine is lesser than the atmospheric pressure during the suction, therefore the negative loop is formed, which is seen in a figure. During the compression stroke, the work is done, that is, gas has been burned, and gas is then compressed, and the higher negative loop is obtained. In the working stroke, that is a power stroke, the fuel combustion, fuel burns, and the large amount of loop, positive loop is created. That is a large amount of energy is get created. And during the exhaust stroke, the work is done on the gases. Therefore, the negative loop is again obtained. A turning movement diagram for the compound steam engine is shown in figure number 3, where 3 cylinders and the resultant turning movement diagrams are as shown, where is the mean line and the resultant movements has been shown. The resultant turning movement diagram is the sum of the turning movement diagrams of all the 3 cylinders. Okay, so the combinations are given, the fluctuations also given, so they can eliminate the vibrations which is occurred by the single cylinder. Okay, so while we are using single cylinder, there like a basic vibration is generated continuously, so that can be eliminated by using this number of, we can increase the number of cylinders and we can reduce the dynamic forces. So in this segment, what we can see, the first cylinder is a high pressure cylinder, second cylinder is an intermediate cylinder, and third one is a lower pressure cylinder. The crank, it can be placed in a particular angle. So the angle between each cylinder is 120 degree. So whatever the dynamic forces has been generated, that can be get eliminated. So in the such segment, what is the maximum fluctuation of energy? How we can calculate it? So refer the multi-cylinder turning moment diagram. So in this turning moment diagram, so initial first area, small a1, that is the curve which is between the point A and B. So that area we can consider as energy. Okay, so each time if it changes the areas, the energy and area get added or subtracted. Which is above the mean line, that we can add, which is below the mean line, mean torque line, we have to subtract. That it means it can above the mean line, the curve above the mean line, which can be added, that is energy is increased with the area, and in below line, that area get utilize the energy. So we need to understand how the energy can be changes from point to point. Now at the point A, there is no initial energy is there, so E is equal to 0 near about. So at figure number point number B, the A to B curve is in above the mean line, so it is a positive. So add area 1. From B to C, the area 2 is negative, so we are subtracting the area. So similarly, plus minus, we can find out till the sixth area. You can see. So the maximum energy fluctuation is E plus A1 and minimum energy fluctuation is E plus A minus B plus A1 minus A2 plus A3 minus A4. So that is the minimum fluctuation. Then maximum fluctuation energy is nothing but the difference between these two energies. Okay, so maximum fluctuation of the energy is nothing but the subtraction, that is a maximum energy in the flywheel minus the minimum energy in the flywheel. So what we get, A2 minus A3 plus A4 is the maximum fluctuation of the energy. So these areas can show the maximum fluctuation in the energy. Now the coefficient of maximum fluctuation, we know the ratio of maximum fluctuation of energy divided by work done is the maximum fluctuation energy coefficient, that is denoted by CE. So maximum work done per cycle is equal to turning torque, that is the mean torque developed multiplied by angular turns in a radian per revolution. So we can calculate the mean torque of IC engine, that by equation P into 60 divided by 2 pi n or P divided by omega. And the work done per cycle is nothing but P into 60 divided by n, where n is the number of strokes per minute. So similarly, you can find out the different coefficient of frictions, fluctuations in the energy for a particular operations. So when we go with the single cylinder double acting steam engine, the coefficient of energy fluctuation is near about 20%. When we go with the cross compound steam engines, only 9 to 10% energy fluctuations is there. When we go with a single cylinder, there are more fluctuation, more than double we can observe. If you go with the four-cylinder IC engine, then again the fluctuation get reduced. As the number of cylinder increases, the dynamic force get reduces and the coefficient of fluctuation of the energy get reduced. Okay, now how energy can be stored in the flywheel? We need to identify. So you can look at the figure number 5, the basic arrangement of the flywheel. Rim is there, hubs, arms, and it is mounted on the shaft. So small m is the mass of the flywheel in kilogram. K is the radius of the gyration. I is the mass moment of inertia for flywheel at the axis rotation, that is mk2. N1 and N2 is the maximum and minimum speed during the cycle, which is in revolution per minute. Omega 1, omega 2, maximum and minimum angular speed during the cycle, that is radian per second. So minimum speed N1 plus N2 divided by 2, minimum angular speed omega 1 plus omega divided by 2, and the coefficient is N1 minus N2 divided by N. Now, the kinetic energy which is generated by the flywheel, that is E is equal to 1/2 into I omega square, or you can say 1/2 mk square into omega square. As the speed of the flywheel changes from omega 1 to omega 2, the maximum fluctuation of energy, that is the delta E, which is nothing but the maximum kinetic energy minus minimum kinetic energy. So maximum kinetic energy 1/2 I omega square, omega 1 square. Minimum kinetic energy 1/2 I omega 2 square, which is shown. So difference between omega 1 and omega 2, we will get the difference. So find what is the final equation, what we get. So I 1/2 I omega 1 minus omega 2, omega 1 square minus omega 2 square. So you can create the byproducts, that omega 1 plus omega 2 into omega 1 minus omega 2. So from the equation, we can resolve this equation through I omega 1 minus omega 2, as we know properly. So based on that, omega is equal to omega 1 plus omega 2 divided by 2. So we have written omega over here, and similarly we can find out the equation for CS, that is omega 2 minus omega 1 divided by omega. So we need to divide, multiply and divide by omega. So what we get, the final equation I omega square into CS. Okay, so it is nothing but twice of ES, that E is equal to 1/2 I omega square. So twice ECS. Now the radius of gyration may be taken equal to the mean radius of rim, because of the thickness of the rim is very small as compared to the diameter of rim. So therefore K is equal to capital R. So when we put the value of K in the equation, what we get, delta is equal to mr square omega square into CS, or mv square into CS. Okay, so this is in a basic equation, the mass of flywheel rim to be determined. Some things we need to be identified that have mentioned over here. In the above equation, only the mass moment of inertia of the ring is considered. The mass moment of inertia of the hub and arm is neglected. This is due to that the fact of a major portion of the weight of the flywheel is on the rim, and the small portion is on the hub and arms. So because of that, the practical application, in the practical point of view, we are considered, and the hub arms are near to the axis of rotation. Therefore, the moment of inertia of the hub and arm is considered to be very small. Now the density of the cast iron may be considered as 7,260 kg per meter square, or for cast steel it may be 7,800 kg per meter square. So actually it's depend upon the material which is chosen. The mass of the flywheel you can calculate by the equation m is equal to volume into the density, that is volume is equal to 2 pi r into area and density rho. The expression may be defined the value of cross area of the rim, assuming the cross section area of the rim is b into t, whereas b is the width of the rim and t is the thickness of the rim. Now we know that the b by t, which is usually taken as a 2 to find out the width and thickness of the rim. When the flywheel is to be used as a pulley, then the width of the rim should be taken 20 to 40 mm greater than that the width of the belt. This point to be noted, because these empirical relations will be help you to easily calculate the dimensions. Now next one, we need to identify the stress in the flywheel ring. The flywheel is we have already seen the areas and the basic parts of the flywheel, which is shown in figure number 6. The major portion of the mass weight of the flywheel is concentrated on the boss or hub for fixing the flywheel on the shaft, and the number of arms to be supported the arm rim to the hub. Okay, so following type of stresses, generally 3 stresses are occurred, that is noted are First one is the tensile strengths due to the centrifugal forces. Then tensile and bending stress caused by the resistance of the arms. And third one is a shrinking stress due to the unequal rate of cooling of the casting. Because of these stresses may be very high, but there is no easy method to determine. So this stresses is taking consideration with the factor of safety. Now we have to find out the two type of stresses which need to be considered. Sinking stress, which we can avoid with the suitable, if you apply the suitable cooling process, then we can eliminate this stress. So major stresses are tensile stress due to the centrifugal force and the tensile bending stress caused due to the resistance of the arm. Okay, so let's see how we can calculate. Tensile stress due to the centrifugal force, that is a stress in the rim due to the centrifugal force. Assume that the rim is unstrained by the arms is to be determined in a similar way as a thin cylinder subjected to the internal stresses. So basic let's consider small b is the width of rim, small t is the thickness of rim, capital A the cross section of area of the rim, that is b into t, d is the diameter of flywheel, r is the mean radius of the flywheel, rho is the density of the flywheel material, omega is the angular velocity of the flywheel, v is the linear velocity of the flywheel, and sigma t is the tensile or hoop stresses. Now, first we need to consider a volume. Okay, considering from figure number 7, the cross section area is to be considered, and we are considering that some angular deflection is occurred, that is delta t. Okay, which is very small element with respect to the volume. The volume of that small element we can calculate by A into R into delta theta. The mass of that small element dm is equal to volume into the density. So volume is AR delta theta into rho. The centrifugal force on that element, that is a small element, that is df, is equal to dm omega square into r, that is dm means rho into a into r into delta theta into omega square into r. So equation of df is equal to rho a r square into omega square into delta theta. Now vertical component of that centrifugal force, the df into sine theta. So putting the value of df and into sine theta, what we get? Rho a r square omega square sine theta into d theta. Now vertical bursting force across the rim of axis of rim diameter along the axis x and y. We find out by taking the integration of the equation. Okay, what we get, the equation is equal to 2 rho a r square into omega square. Now vertical forces is resisting by the force of 2p, which is shown in which is can calculated as 2p into 2 omega t rho t, that is a tensile stress into area. So from equation 1 and 2, when we equate, because it's both vertical forces are there, so we can equate these equations. So twice rho a r square into omega square is equal to 2 sigma t into a. So the tensile stress we can calculate from this is sigma t is equal to rho r square into omega square, that is nothing but r square omega square is nothing but the v square. So similarly you can find out the sigma t, that is the stresses induced. Now we can go with the second one, the tensile bending stress caused by the resistance of the arms. The tensile stress tensile bending combination stresses in the rim due to the resistance of arm is based on the assumption that each portion of the rim between the pair of arms behaves like a beam, that is a fixed beam at the both ends and having a uniformly loaded, which is shown in figure number 8. Okay, the length between the fixed ends L is equal to pi d by n, where n is the number of arms. The uniform, that is UDL per meter length, will be equal to the centrifugal force between the pairs. W is equal to BT rho omega square R. Now the maximum bending stress M is equal to as it is considered as a fixed UDL. So omega L square divided by 12, that UD will load, BT rho omega square R divided by 12. Then L is equal to 2 pi R divided by N bracket square, where 1/2 BT square is nothing but the section modulus. So the bending stress sigma B is equal to M by Z. Putting all the values, what you get? 19.74 rho V square R V square into R divided by N square into T. So the total stress acting on the rim is sigma plus sigma T plus sigma B. Okay, if the arms of the flywheel do not stretch at all, are placed very close to each other, the centrifugal force will not be set up in the rim, and thus the sigma t will be 0. In other hand, if the arms are stretched enough to allow free expansion of the rim due to the centrifugal action, there will be no resistance due to the arm. So sigma b will be 0. So hence it means that we need to increase the number of rims to avoid this. Okay, so it has been shown by Mr. G. Lenza. The arm of the flywheel stretches about to 3/4 of the amount of the necessary of free expansion. So therefore, the total stress in the arm is 3/4 of sigma t and 1/4 of sigma b. So equation gets changed, that is rho v square into bracket 0.75 plus 4.935 r divided by n square into t. Okay, so now we have calculated the stresses in the flywheel rim. Now next one is a stresses in the flywheel arm. So again, these three stresses we have already discussed. We have seen the equations. Okay, so next one is the design of shaft, hub and key. Now shaft is designed based on the torque. Okay, hub is also based on the torque, and the key, which is based on the torque. Okay, key is obtained with the equation that T max is equal to n into w into tau into d1 by 2, where L is the length of the key and D is the diameter of the shaft. Now, how actually constructions, there are different type of constructions are available of the flywheel into the market. We will discuss the construction. Okay, and in next lecture we will discuss the numerical on the flywheel. So the flywheel is similar to that of, it's in a single piece. Okay, up to the 600 diameter, it can be manufactured in a single piece, that is based on the casting operation. Okay, the rib and hubs are joined together by means of the wave, as shown in figure number 11a. The holes in the wave may be made by handling purpose, because we have to lift these rims as the flywheel is get larger. In the case of the flywheel, a larger size, that is about the diameter of 2.5 meters, The arms are made with the wave, which is shown in figure number B. So the weight, as the flywheel is small, it is made with the particular to increase the strength. Okay, it is solid one. It means that the material which is included, that is appropriately, you can see in figure number 11E. In 11B, we can see that if the size of flywheel get increases, now the weight is also get increases, but we have to maintain same strength and reduce the weight by reducing by appropriately design this flywheel. Okay, you can see the design change in small size and bigger size. The flywheel which is greater than, having a diameter greater than from 2.5 meter onwards, that can be manufactured in two pieces. Okay, you can just join it from figure number 12, that is called as a flywheel. Okay, the diameter having more than 2.5 meter, which is that flywheel can be manufactured or cast in two pieces. Okay, so that can be called as a split flywheel. The advantage of this kind of flywheel, split flywheel, is relieving the shrinking stress in the arm due to the unequal rate of cooling of the casting. A flywheel is made in two walls, halves should be split at the arms rather than the between the arms in order to obtain the better strength of the joint. Okay, you can see in figure number 12. The shrinking links. Okay, now these are two hulls or two parts are be joined with these shrinking links. The width and the depth of the shrinking links is also considered or taken as 1.25 to 1.35 times of the thickness of the link. The slot in the rim into which the link is to be inserted are made slightly larger than the size of link. Okay, how these shrink links are developed, you can look at over here how they are joined. The relative strength of the rim joint and the solid rim is given in the table. If solid rim is there, they have very high strength. Flangeless joint, if we are utilized, then 25% only the strength is in between. Then shrink link, if we are using, then it's a 60% that get increased. If we are using quarter type of joint, which is shown in figure number 12, that increases the maximum strength of this two pieces joint. Okay, so thank you for this. That much is the theory related to the flywheel. Now in the next lecture we will discuss the problem or numericals related to the flywheel. Okay, so thank you for joining the lecture.